Okay, class, here we go. This one's going to be a pretty long one, so just buckle up and let's get going. Today we are going to talk about solids and understanding the structure that makes up our solids. Not just saying, okay, solids are tightly packed together, but being able to understand how atoms orient themselves within a solid. So our learning objective for today would be that we can illustrate how atoms within solids orient themselves in 3D space. In saying that, let's dive in. Okay, before we get any deeper into stuff, let's review and talk about the particle theory. Okay, the particle theory of matter is the model that describes the arrangement and movements of particles within a substance. This model is used to explain the physical properties of solids, liquids, and gases. As we've discovered in prior videos and classes, we know that solids have a fixed volume and shape because their particles are closely bound together or tightly packed. Solids cannot move past one another, so they cannot be compressed. Solids orient themselves in regular patterns. That was going to be big for later. And their particle movement is a result of atomic vibration. Our gases have molecules that are spaced far apart, so they're not really bound to one another. Because of this, they take the volume of whatever container they're in. Gas particles arrange themselves randomly in whatever container they're in, resulting in gases not having a fixed shape. Out of all the states of matter, gases have the fastest moving particles, thus they have the highest amount of energy within each particle. Finally, our liquids are the intermediate state between the extremes of the solids and the gases. Liquids are loosely bound together, which allows them to move past one another and orient themselves in the shape of the container they are in. Because these molecules are still bound together, though, these molecules have a fixed volume despite having a variable shape. The amount of energy stored within these particles is intermediate between these solids and the gases. It has more energy than the solids, but less energy than the gases. Today we're going to take a deeper look into the structure of solids. In some solids, atoms or molecules form a repeating pattern in all three dimensions. This makes the internal structure of a solid highly organized and consistent. We call these types of solids crystalline solids. If we are wanting to take these repeating units within a crystalline solid out and model the structure, we would call that structure a crystalline lattice. Keep in mind this arrangement is still bound by Coulomb's law, so each individual atom will orient itself so that it minimizes repulsive forces and maximizes attractive forces within the solid. We can represent the crystalline lattice with a small collection of atoms, ions, or molecules called a unit cell. Think of the unit cell as a small repeating section of the entire crystal lattice. Because many different types of unit cells exist, we often classify the unit cells by its symmetry. We are going to spend our time focusing on a cubic unit cell. There are three types of cubic unit cells we are going to go over today. The first cubic unit cell that we are going to go over today is the simple cubic unit cell. This consists of a cube with one atom in each corner of the cube. The atoms touch each other along each edge of the cube, so the edge or length of the cube is twice the radius of one atom. A characteristic feature of any unit cell is the coordinate number, or the number of atoms in which each atom is in direct contact with. Because these atoms are within direct contact with each other, the coordinate number is also the number of atoms in which a particular atom can strongly interact with. A simple cubic unit cell has a coordinate number of 6. This means one atom within a simple cubic is always in contact with at least 6 other atoms. Finally, a simple cubic cell has a packing efficiency of 52%. This means the 52% of the total cubic cell is occupied by some portion of an atom. The second type of unit cell that we're going to talk about is body-centered unit cells. This one consists of one atom in each corner of the unit cell and the same type of atom within the center of the cell. Note that the atoms along the corners within this type of cell are not touching each other. Okay, so that's going to change the length of each edge. The coordinate number for these types of cubic cells is 8. And because we have something in between all four corners, now we have a higher packing efficiency. So the packing efficiency is now 68%. Our final type of unit cell is the face-centered cubic unit cell. This type of unit cell consists of one atom along each corner of the cube and one atom within the center of each face of the cube. Face-centered cubic unit cells have a coordinate number of 12 and a packing efficiency of 78%. Now that we got that out of the way, we can talk about the type of crystalline solids and the crystalline solid hierarchy. Our three major branches of the crystalline solid hierarchy is molecular solids, ionic solids, and atomic solids. And they are going to be differentiated by the individual units that make up these solids. Our first one is molecular solid. Molecular solids are those solids whose composite units are molecules. The lattice sites in the crystalline molecular solids are occupied by molecules or compounds. Molecular solids are held together by the following: weak intermolecular forces, dispersion forces, dipole-dipole forces, and hydrogen bonding. Molecular solids as a whole tend to have lower melting points, but if there is a strong intermolecular force involved, such as hydrogen bonding, these melting points can increase. These solids typically do not pack their molecules efficiently within a unit, so they can be soft and have a low density. Molecular crystalline solids also lack ions and free electrons within their structure, so they are going to be poor conductors of heat and electricity. Two examples of molecular solids would be diiodine, whose melting point is 114 degrees Celsius, and ammonium, whose melting point is negative 78 degrees Celsius. Notice the difference in melting points and how efficiently these molecules are packed together within the unit. That's going to play a key role in determining physical properties. Ionic crystalline solids consist of alternating positively charged cations and negatively charged anions. These ions that make up the unit cell can be monoatomic or even polyatomic. The most common type of ionic crystalline solids are a combination of the group 1 or 2 metals, or your group 16 or 17 nonmetals, or a non-metallic polyatomic ion. Typically, ionic crystallines are hard and brittle while having a high melting point. In the solid state, these structures do not conduct electricity well, but when they are converted to their aqueous state, are very good conductors of electricity because they have ions. These structures optimize their unit packing efficiency, so these structures can be relatively dense. Some examples of an ionic crystalline are sodium chloride, who has a melting point of 108 degrees Celsius, and calcium fluoride, who has a melting point of 1418 degrees Celsius. We consider solids whose composite units are individual atoms to be atomic solids. Solid iron, solid xenon, and silicon dioxide are examples of atomic solids. Depending on the type of interaction between the atoms within a solid, atomic solids can be broken down even farther into 3 groups, called the non-bonding group, the metallic group, and the network covalent group. So our non-bonding atomic solids. Non-bonding atomic solids are the atomic solids that are held together by relatively weak dispersion forces. In order to maximize these interactions, non-bonding atomic solids form closely packed structures so that they can maximize their coordinate number and minimize the distance between atoms. The only non-bonding atomic solids are noble gases in their solid state. So an example of this would be argon, which has a melting point of negative 186 degrees Celsius. Our metallic atomic solids are solids that are held together by metallic bonds, which in the simplest form represents the interaction between metal cations and a sea of delocalized electrons surrounding them. This sea of electrons do not belong to one particular atom, but are capable of moving through the entire crystal. This results in a metallic atomic solid that is a great conductor of electricity. Since the metallic bonds are not directional, in other words, the chemical bond between each metal is omnidirectional, these atoms are closely packed to each other. Metallic bonds have varying strengths, so some metals such as mercury have melting points below room temperature, while other metals such as iron have a really high melting point, which is 1809 degrees Celsius. Our last type of atomic crystalline solids are our network covalent atomic solids. The network covalent solids, such as diamond and silicon dioxide, are held together by covalent bonds. The crystalline structure of these solids are more restricted by geometrical constraints of covalent bonds, so they do not tend to form closely packed structures. These solids tend to be hard and brittle because they have a fixed geometry that comes from their bonds. For example, in diamond, each carbon atom is formed into a tetrahedral geometry because it is bound to 4 other carbon atoms. This makes our structure inflexible and creates strong bonds. The inflexibility leads to a relatively low density. Also, because of the strength of the bonds, the network covalent crystalline solids have a really high melting point. Finally, because these solids are made up of atoms and not ions, it does not collect electricity at any state. Before we conclude this video, we have one more thing to talk about, and that is alloys. An alloy is a mixture of metals or a mixture of metals plus some other element. There are 2 main types of alloys, substitutional alloys and interstitial alloys. Substitutional alloys occur when a metal alloy is formed by substituting one metal for another metal of a similar size or just a tiny bit smaller. In order for a substitutional alloy to occur, both atoms being substituted need to be similar in size. In fact, the size differentiation between the original atom and the atom being substituted for cannot be greater than a difference of 15%. Bronze is probably the best example or best known alloy that is a substitutional alloy. Bronze consists mainly of copper and tin. Both these metals work together to make the solid bronze, which has a crystalline structure as shown here. Notice when we combine our copper and tin together, each atom is roughly the same size, so they are able to interchange with one another and create a new crystal lattice. Our interstitial alloys are alloys formed by inserting small atoms into holes within the metal structure. As stated earlier, metallic structures are structures that consist of large positively shared ions and delocalized electrons. For an atom to be inserted into a lattice structure, these atoms must fit into the space between the metal lattice or between the metal atoms. Usually only small atoms such as hydrogen, carbon, boron, and nitrogen can fit into these metal lattices. When an atom inserts itself into a metal lattice to form an interstitial alloy, they go through a process called the interstitial mechanism. Note, since these atoms are placed in a spare space between the metals and are significantly smaller than the metal atoms, these alloys cannot go through substitution, but instead are trapped in the space between large atoms called interstices. An example of an interstitial alloy is steel. Steel is nothing more than iron atoms tightly bound together with small carbon atoms filling in the empty spaces between the irons. As we can determine from our example of steel, because the structure is highly packed together, it is extremely hard and the bonds are not easily broken. In other words, this alloy is very strong. Now that we have both those out of the way, we are able to tell the difference between the types of alloys and the unit cells illustrated within the AP test. Just remember, when in doubt on alloys, the main difference between a substitutional and interstitial alloy is that a substitution alloy is formed by substituting one metal for another metal of a similar size, while an interstitial alloy is formed by inserting small atoms into the spare spaces of the metal lattice structure. Also, knowing the unit cell and the types of atoms or molecules that make them up will point us in the right direction in determining the type of crystalline solids a substance is. Knowing these types of solids will help us predict the properties and behaviors of that solid. in saying all that, I think that's enough for y'all today. So keep up the good work in class, and see you next time.